Good day, doctor. My name is Tan Pik Ling from Group 6 for the Thermodynamics and Material Engineering Laboratory. So I will be explaining about this torsion of bar experiment 6. This is our group member. We have Sri, me, Pik Ling, Dave, is me, and also Zafran. So this is the content for this experiment. We will be talking about the abstract and introduction, and then Izzy will explaining the theory. Zafran will talk about the procedure. Dave will talk about the result, and Sri will talk about the discussion. And at last, Dave will talk about the conclusion. So abstract. In the era of fourth industrial revolution, or maybe we call it IR 4.0, actually full of the advanced machine and also technology. So many of the components and also products are actually related to torsion force. So in order to ensure the quality of the equipment, component, and also the product, the torsion testing machine are actually used to test on all these. So in this experiment, we will investigate the relationship between the torque and then the angle of twist, as well as the of the circular cross-section specimen, and will be also determine the modulus of rigidity of the materials, which is the aluminum alloy, steel, and also nylon. So the data is then collected in this experiment, and it will be used to plot the graph of the angle of twist against the torque. And moreover, the modulus of rigidity is also calculated and will compare with the theoretical value. So this is the objective of this experiment, which is to investigate the relationship between torque and the angle of twist of a circular cross-section specimen. And the second objective of this experiment is to determine the modulus of rigidity of the material. So this is the introduction for this torsion of bar. So consider there is actually a circular shaft that is attached to a fixed support at one end. When a torque is applied to the other end, the shaft will free and rotating through an angle called the angle of twist. So torsion is actually analyzed through the stress and also strain in members of circular cross-section subjected to twisting couples or torque. These couples have a common magnitude and also opposite senses. They are vector quantities and can be represented either by curved arrows as shown in this figure or by the couple vectors. So members in torsion are encountered in many engineering applications. The most common application is provided by the transmission shaft, which is actually used to transmit power from one point to another point. So for example, a shaft is used to transmit power from the engine to the rear wheel of an automobile. So this shaft can be either solid or hollow. So consider the small square element formed by two adjacent circles and two adjacent straight lines traced on the surface of a cylinder of radius before any load is applied. So as the shaft is subjected to a torsion load, the element deforms into a rhombus. So that's all from me. I will pass the space to Izzy.
My name is Aizuddin binti Azmi, and I will explain about theory. So torsion is actually a twisting of an object when we apply torque towards the object. The torsion will cause a twisting stress we call as shear stress, and a rotation we call as shear strain. This, if we apply a torque or a moment to the end of a circular bar, it will cause the bar to twist to an angle we denoted as theta, where this angle is actually a function of the bar length L and also the shear modulus G. The angle will start at 0 and it will increase linearly as a function of x, where the rotation or the shear strain will be constant along the length. If we apply a moment along a longitudinal axis of a shaft, the angular deformation in the shaft will be observed, which we call as the angle of twist theta. So in order for us to observe or to calculate this angle of twist, we can use the formula of theta equal to torque times length divided by G times J, where J is the polar moment of inertia, by using the formula of pi times C2 to the power of 4 minus C1 to the power of 4 divided by 52, and the C is actually the cross section of radius.
Hello everyone, my name is Zafran and I'll proceed with the apparatus and methodology. For the apparatus part, 5 Newton, we have 5 Newtons load, ruler, 1 Newton loads, vernier caliper, clamp, torsion bar, hanger cord, ball bearing in the housing, steel, aluminium alloy, and nylon rod, and lastly we have spanner. So this is all the apparatus that we're gonna be using in this experiment. Next, we have methodology. The aluminium alloy rod was clamped in position and load hanger was placed on the cord. The rotational scale was set up at 400 mm from the fixed clamp and its pointer was fixed to 0 before it starts to read. After that, the twists of each specimen were recorded for every 5 Newtons increment until it reached 40 Newtons weight. And then, the load were removed and the position of the rotational scale together with the pointer was changed to over 200 mm from the clamp position. After that, the procedures were repeated. The diameter of the specimen were measured and recorded using vernier caliper. The specimen was changed to steel rod and the experiments were repeated from 400 mm in length only. The nylon rod was clamped in the position and the twist for 200 mm and 400 mm was measured when the load of 5 newtons by increment of 1 newton was applied to the torsion head. After that, the loads were removed and the occurring of full elastic recovery was recorded. That's all from me.
Hello everyone, my name is Devraj Ravi. I made to explain the result of our experiment. There are total 3 tables. Table 1, data for aluminium alloy rod. As we see in this table, the torsion height effective diameter, the diameter and the twist of rod over 400 mm and over 200 mm were recorded during the experiment. The thing that we need to find is the torque over 400 mm and over 200 mm. The formula that we are going to use to find this torque is take the torsion height effective diameter, divide by 2 and times with its respective hanger load. Let's calculate one example, which is the torque over 400 mm for its hanger load, which is 5 Newton. So we take its torsion height effective diameter, which is 77 mm, divided by 2 and times with its hanger load, which is 5. Then we get 187.5 mm. It goes same for all hanger load until 40 Newton, and it goes same to torque over 200 mm. The next table is data for steel rod. It goes the same formula, but in this case there is no twist or 200 mm and torque over 200 mm, just 400 mm. For table 3, they are both, which is over 400 mm and for 200 mm for data for nylon rod. It goes the same formula too. Then we complete the 3 table. Next, we need to plot a graph for each table. The values that we need to use to plot the graph is the torque over 400 mm and over 200 mm and twist over 400 mm and over 200 mm. Except for the data for steel rod, we just need to use the torque and twist over 400 mm. So the x-axis will be the torque and the y-axis will be the twist of rod. In table 1 and table 3, in the graph there will be 2 lines because they one for over 400 mm and one for over 200 mm. Whereas for table 2, which is for steel rod, there will be 1 line because there is only one which is over 400 mm. That's all from me. Thank you so much.
Hey everyone, my name is Srisan and I am going to explain about the discussion of this experiment. So the first question was, to what extent does the experiment verify the torque or twist formula based on the graph plotted? So these are the graphs that we plotted. The first one is the angle of twist versus the torque of aluminium alloy rod. The next is the angle of twist versus the torque of steel rod. And the third one is the angle of twist versus the torque for nylon rod. So based on the graph above, it is shown that the torque is directly proportional to the angles of twist of aluminium alloy, steel and nylon. Each graph proves a linear relationship between torques and the angle of twist of the 3 materials. In simpler words, when torque applied increases, so the angle of twist increases as well. Besides that, it showed that the gradient of graph for nylon was larger compared to steel and aluminium alloy due to the largest rigidity of nylon. Thus, nylon can be twisted more when the same load is hanging on it. From this experiment, the value for the modulus of rigidity was calculated for 3 rods. The modulus of rigidity can be determined by G equal to torque times by the length of the shaft divided by polar moment of inertia times by the angle of twist, which is also equal to length of shaft divided by the gradient of the graph times by the polar moment of inertia. Based on the formula, it is proven that the modulus of rigidity is inversely proportional to angle of twist but directly proportional to torque. So, now for the modulus of rigidity for steel rod, we have the gradient of the graph, which is M 400 mm is equal to 0.0106. The polar moment of inertia J can be calculated by pi times by d power of 4 divided by 32. So, the answer is 60.87 mm power of 4. Next, the modulus of rigidity, which is equal to 400 divided by 0.016 times by 60.87, then times by 180 over pi to change it in radian, and the modulus of rigidity for the steel rod is 35,520.1410 Newton per millimeter square. So, next, the modulus of rigidity for aluminum alloy rod is, we have two gradient where the M for the gradient for 400 mm is 0.098 and the gradient for 200 mm is equal to 0.049. Then we have to calculate the polar moment of inertia J is equal to 155.639. Then we have to find two modulus of rigidity since we have two types of length, which is for 400 mm and 200 mm. So the 400 mm, the modulus rigidity is 14,962.8.441 and the modulus of rigidity for 200 mm is 40,962.8441. So now we have to find the average modulus of rigidity among them. So the average is the modulus of rigidity for 400 mm and the modulus rigidity for 200 mm are summed up and divided by 2, and the answer for the modulus of rigidity, the average modulus of rigidity is 14,962.8441 Newton per millimeter square. Next, same goes to this nylon. The modulus of rigidity for nylon can be calculated by getting the gradient of the graph for 400 mm, which is 0.03634, and the gradient for 200 mm is 0.01783. Then calculate the polar moment of inertia, which is 177.96 mm power 4, and then calculate the modulus of rigidity for 400 mm, which is 3,543.5747 Newton per millimeter square, and then the modulus of rigidity for 200 mm is 3,611.7204 Newton per millimeter square, and then the average modulus of the rigidity is 3,577.6476 Newton per millimeter square. Based on the calculation, the results have a bigger difference with the theory, where according to the handbook values for modulus rigidity are 26,200 Newton per millimeter square for aluminum alloy, and about 79,000 Newton per millimeter square for steel, and 75,000 Newton per millimeter square for nylon. So that proves that the conducted experiment does not verify the torque over twist formula. The huge difference between the experimental and theoretical value might be due to the errors that occur when conducting the experiment. So, to prove that, we have done the percentage of error for the three materials. So, the first percentage error for the aluminum alloy was 42.89%, and percentage error for the steel is 55.04%, and the percentage error for nylon was 95.23%. From the table of percentage error, there is high percentage errors which shows that errors occurred when conducting the experiment. Firstly, parallax error occurred when taking the reading of angle of the scale. In order to get more accurate reading, the observer should place his eyes perpendicularly to the scale. Next, the rod used might not be pure, which could affect the results. To minimize this error, make sure use a new rod without any deformation, which could affect the results. Lastly, environmental factors such as temperature or wind might also affect the results. Thus, conduct the experiment in controlled conditions to minimize the environmental factor to obtain a more accurate result. Thank you.
So as for conclusion, we can see from the graph obtained in the discussion part, where the greater the torque applied, the greater the angle of twist theta. Hence, this relationship verifies the angle of twist formula. We can also get the modulus of rigidity G for steel rod is 35,520.1410 N over millimeter squared. Aluminum alloy rod is 14,962.8441 Newton per millimeter squared. And for the nylon rod is 33,577.6476 Newton per millimeter squared. However, these experimental values G that we obtain in this experiment are quite vary with the theoretical values of G. This is because of some parallax error that occurred during this experiment. So, these are our references that we use in this experiment. So that's all from us. Thank you.